Hi, my name is Vic, and today we're going to be predicting the stock market using machine learning. We'll start out by downloading data on the S&P 500 index, then we'll clean the data up and use it to train a model, then we'll do backtesting to actually figure out how good our model is, and we'll add in some more predictors to improve our accuracy. We'll end with some next steps that you can use to continue improving the model on your own. It's going to be a really fun and exciting project. Before I started DataQuest, I actually spent a lot of time predicting the stock market, both winning machine learning competitions and developing and selling algorithms. There are a lot of real-world considerations when you're predicting the stock market that not all tutorials will show you. So I'm going to show you those today so you can build a higher quality project. Let's dive in. By the end of this project, we will have created a machine learning model that can predict tomorrow's S&P 500 index price given historical data. We'll also have backtested this model on 20 plus years of historical data, so we can really be confident in the predictions that it's making. Okay, let's go ahead and get started. We're going to be using Jupyter Lab for this project. You can also use Jupyter Notebook if you have it installed. And the first thing we'll do is we'll import something called the yFinance package. This package calls the Yahoo Finance API to download daily stock and index prices. And the first thing we'll do is we'll initialize something called a ticker class, which will enable us to download price history for a single symbol. In this case, we will use the GSPC symbol, which is the S&P 500 index. So we'll go ahead and run that. And then the next thing we'll do is we'll go ahead and query the historical prices. So we'll use the history method and we'll pass in period equals max, which will query all data from the very beginning when the index was created. So let's run that. And we actually end up with a pandas data frame, which is very, very nice. And in this data frame, each row is the price on a single trading day. So non-trading days are not included in this data. And the columns are the opening price, so the price when the market opened, the highest price during the day, the lowest price during the day, the closing price when the exchange closed, and the volume, so the total volume that was traded that day. So we're essentially going to use these columns to predict if the stock price will go up or down tomorrow. We also have these additional columns, dividends and stock splits, but we're not going to use these and we'll actually remove them later. All right, so we'll take a look at the index of the S&P 500 data frame, and we can see we have a date time index, and the index is this column on the left, if you're not familiar with it. And that column will enable us later on to really index and slice the data frame easily. All right, so the first thing we'll do is we'll go ahead and plot the data in the data frame. So we'll plot the closing price against the index. So what this is doing is it's saying show the index, which is really the trading days, the dates on the x-axis, and show the closing price on the y-axis. So we can run that, and we get a nice chart of the S&P 500 price history. And we really can regret not buying the index fund at any point in the last few years. All right, we'll do a slight bit of data cleaning here. We'll just remove those extra columns that we don't need. So we'll go ahead and remove the dividends column, and we'll also remove the stock splits column. These columns are more appropriate for individual stocks, not an index, so we don't actually need them. And then the next thing we're going to do is set up our target. So this is what we're actually going to be predicting using machine learning. So this target is going to be, will the price go up or down tomorrow? So some people like to predict the absolute price. So trying to predict if the stock price will be $17 or $18 tomorrow. The big problem with that is your model can be extremely accurate. You can be very good at predicting the absolute price, but you can still lose a ton of money because ultimately, if you're buying and selling stocks, you don't care about getting accurate on the absolute price, right? You care more about getting accurate on the directionality, if the price will go up or down. So you know, can I buy the stock and then will it go up? You can be really close to predicting the actual price and in fact be very far behind on predicting if the stock will go up or down. So what we're going to try to do is say on days that the stock goes up, can we actually predict that it will go up? And that way, if we want to buy the stock, we know we can buy it and the price will go up. So our target is going to be, will the stock go up or down? So first we're going to create a column called tomorrow. And basically what this column is going to be is it's going to be tomorrow's price. And we'll use the pandas shift method to help us do this. So let me run this and then show you what actually happened. So we took the close column and then we shifted all the prices back one day. So you can see for January 3rd, 1950, the tomorrow column is now the price on January 4th, the closing price. So we now have a column that shows tomorrow's price. Then based on tomorrow's price, we can now set up a target. So the target is what we're going to try to predict with machine learning. And really all we need to do with the target is tomorrow's price greater than today's price? So this will basically return a Boolean indicating if tomorrow's price is greater than today's price. But we want to actually convert this to an integer so we can use it in machine learning. So we're going to use the asType method and pass in integer. Okay, asType or asInt. So now we're going to show the S&P 500 data frame. And we can see we now have a target column that is a 1 when the price went up. So that's when tomorrow's price is greater than today's price. And it is a 0 when the price went down. And this is what we're going to try to predict. The next thing we'll do is there's a lot of historical data in this data frame. And usually a lot of historical data is great. But with stock market data, if you go back too far, the market could have shifted fundamentally, and some of that old data may not be as useful in making future predictions. So what we're going to do is we're going to remove all data that came before 1990. So we are going to use the pandas loc method, LOC, and basically say only take the rows where the index is at least 1990, January 1st. And we can take a look and see what happened. And you can see there are only dates after January 1st, 1990. Now, I wrote .copy here, and I wrote the .copy because if you don't, you can sometimes get a pandas setting with copy warning when you try to subset a data frame and then later assign back to it. So the .copy helps us avoid that. Okay, so we've now set up our data and we can actually start to train our first machine learning model. So let's go ahead and do that. And for our initial model, I'm going to use something called a random forest classifier. I love to use random forest as my default model for most machine learning for a few reasons. So one, random forests work by training a bunch of individual decision trees with randomized parameters and then averaging the results from those decision trees. So because of this process, random forests are resistant to overfitting. They can overfit, but it's harder for them to overfit than it is for other models to overfit. They also run relatively quickly, and they can pick up non-linear tendencies in the data. So for example, the open price is not linearly correlated with the target. For example, if the open price is 4,000 versus 3,000, there's no linear relationship between the open price and the target. If the open price is higher, that doesn't mean the target will also be higher. So our random forest can pick up non-linear relationships, which in stock price prediction, most of the relationships are non-linear. If you can find a linear relationship, then you can make a lot of money. So we're going to initialize our model. And we're going to pass in a few parameters. So n estimators is the number of individual decision trees we want to train. The higher this is, Generally, the better your accuracy is, up to a limit, right? You can't just get free accuracy by making this higher and higher. I'm going to set it pretty low just so this runs quickly for us, but you might want to try with a higher value. Min sample split. This helps us protect against overfitting. Decision trees have a tendency to overfit if they build the tree too deeply. If you don't know much about decision trees, don't worry about it. But setting min sample split helps us protect against that overfitting. The higher we set it, the less accurate the model will be, but the less it will overfit. So you may want to experiment with this and just find the optimal number. And then I'm going to set random state equal to 1. So a random forest, as you may have guessed, has some randomization built in. So setting a random state means that if we run the same model twice, the random numbers that are generated will be in a predictable sequence each time using this random seed of 1. So if we rerun the model twice, we'll get the same results, which helps if you're updating or improving your model and you want to make sure it's actually the model or the something you did that improved error versus just something random. Okay, now we're going to split our data up into a train and test set. Now, this is time series data. And with time series data, you can't use cross-validation. Or you can, but if you do, then your results will look amazing when you're training and horrible in the real world. And the reason why is if you use cross-validation or another way to split up your training and test set that doesn't take the time series nature of the data into account, you will be using future data to predict the past, which you just can't do in the real world and will result in something called leakage, where you're leaking information into the model. So if I asked you to predict the stock price tomorrow and I gave you what the stock price is going to be in 30 days, you would probably do better at predicting the stock price tomorrow than if I didn't tell you anything about the future. So we want the model to actually learn how to predict the stock price, not just randomly happen to have some knowledge about the future that we're not going to have in the real world. All right, so the way we're going to split this data set up is we are going to put all of the rows except the last 100 rows into the training set. And we're going to put the last 100 rows into the test set. I'll show you a more sophisticated way to actually split this up and measure error later. But for now, we're just creating a simple baseline model. And this is the easiest way to do the split. And then predictors. So I'm going to create a list with all of the columns that we're going to use to predict the target. Now, I like to be really explicit about predictors because I've been burned before by just using all of the columns as predictors and then creating a model that looks amazing when I'm training it, right? Like 100% accuracy, but then in the real world doesn't work. What's really easy to do is accidentally use the tomorrow column or the target column even to predict the target. And then what's happening is your model actually knows the future, right? Which isn't going to happen in the real world. All right, so we're going to use close, we're going to use volume, open, high, and low. So those are going to be our predictors. And then what we're going to do is we're going to go ahead and fit the model. So model.fit, train predictors. So this is using these predictor columns. And then we are going to try to predict the target. So this is going to train the model. We're using the predictor columns in order to predict the target. So let's run that, and that'll take a little bit to run. Now, once it's finished, our next step is actually to measure how accurate the model is. This is a really important piece of machine learning, right? You need to measure if your model is doing what you think it is or not. So we're going to import, again, from scikit-learn, we're going to import something called precision score. And all the precision score is it's saying when we said that the market would go up, when the target was a 1, did it actually go up? So what percentage of the time when we said the market would go up, did it actually go up? And this is actually a really good error metric or accuracy metric for this particular case, because I'm going to assume in this case that we want to buy stock. And when we buy stock, we want to hold that stock and then sell it. And we want to make sure that when we buy stock, the stock price is actually going to increase. So depending on what you want and what your goals are, you may want to adjust kind of what error metric you're using to measure performance. But in this case, we're going to use precision score. So we're going to generate predictions using our model with the predict method, and we'll pass in our test set with the predictors. So that's going to generate predictions. These predictions are in a NumPy array, which is a little bit hard to work with. So we're actually going to turn this into a pandas series. And we're going to use the same index as our test data set. I have to import pandas. So we're going to import pandas and then create this series. And we can see predictions is now a series, and it's a little bit easier to read. And then we'll go ahead and actually calculate the precision score. So we'll calculate the precision score using the actual target and the predicted target. And we can see this is not a very good precision score, right? So when we said the stock price would go up, it only went up 42% of the time. That's not great. We'd be better off actually trading against this model, doing the opposite of what it tells us to do. But that's okay. We're going to make this model better, and we will be able to get more accurate predictions. Okay. So the next thing we'll do is we'll just quickly plot our predictions. And in order to do that, we will combine our actual values with our predicted values. And we'll use the pandas concat function to do that. So we're concatenating our test target, which is our actual values, and our predicted values. And then we're going to pass in axis equals 1, which means treat each of these inputs as a column in our data set. Now what we can do is we can plot this. And what this shows us is the orange line. 0 is our predictions, and the blue line is what actually happened. So we can see we mostly predicted that the market would go up, and mostly it seems to have gone down. So that explains why our predictions were so far off. All right, the next thing we're going to do is build a more robust way to test our algorithm. So currently, we're only able to test against the last 100 days. But if you're really building a stock price model and you want to use it in the real world, you want to be able to test across multiple years of data, right? Because you want to know how your algorithm is going to handle a lot of different situations. That gives you more confidence that it'll work in the future. So what we're going to do is we're going to do something called backtesting. And in order to enable backtesting, the first thing we'll do is create a prediction function. And this will basically just wrap up everything we just did into one function. So it's the fitting of the model using the training predictors and the target. It's generating our predictions, which is just model.predict, test predictors. Then it's combining our model into a series, which I'll actually just copy and paste. The only difference here is I gave the series a name, predictions. And then finally, it's combining everything together. Same thing we did before. And then at the end, we'll return our combined data frame with the actual values and the predictions. Now what we can do is write a backtest function, which takes in our S&P 500 data, a machine learning model, our predictors. It also takes in a start value, which we'll set to 2,500, and a step value. So what is this start value? So when you backtest, you want to have a certain amount of data to train your first model. So every trading year has about 250 days. So this is saying take 10 years of data and then train your first model with 10 years of data. And the step is 250, which means that we will be training a model for about a year and then going to the next year and then going into the next year. So what we're going to do is we're going to take the first 10 years of data and predict values for the 11th year. Then we'll take the first 11 years of data, predict values for the 12th year. Then we'll take the first 12 years of data, predict the values for the 13th year, and so on. And this way, we'll actually get predictions for a lot of different years and be able to have more confidence in our model. All right, so in this backtest function, we're going to create a list called all predictions. And that will be a list of data frames, where each data frame is the predictions for a single year. And then we are going to create a function to loop across our data year by year and make predictions for all of the years except the first 10 or so. And then we'll split up our training and our test data. I'm going to use the .copy to avoid that setting with copy warning. And this code is doing exactly what I mentioned. It's creating the training set and the test set. The training set is all of the years prior to the current year, and the test set is the current year. Then we'll use our predict function to generate our predictions. Train, test, predictors, and model. Then we're going to append to all predictions. We're going to append our predictions for the given year. And then at the end, we're going to concatenate all our predictions together. So concatenate can take a list of data frames and combine them all into a single data frame. So let's go ahead and run these. And then what we can do is backtest for our S&P 500 data with the model we created earlier and with the predictors we created earlier. And after we finish the backtest, we can actually start evaluating the error of our predictions. So first, let's take a look at predictions and see how many days we predicted the market would go up versus down. So value counts will just count up how many times each type of prediction was made. So we can see we predicted that the market would go down on about 3,000 days. We predicted the market would go up on about 2,000 days. And now we can actually look at our precision score. And we can take the target and we can take the predictions. And this will give us our precision score. Okay, so across all of these rows, these about 6,000 or so trading days, we were about 53% accurate, precise. So when we said the market would go up, it went up 53% of the time. Now, is that good or not? So as a benchmark, what we can look at is the percentage of days where the market actually went up. And to do that, we can look at the value counts of the target divided by the number of rows total. And this will give us percentages. So the S&P 500 in the days we were looking at actually went up 53.6% of days and went down 46.3% of days. So if all we had done was just wake up every day and say, I'm going to buy and sell at the end of the day, we would actually have been better off than using this algorithm. This algorithm performed a little bit worse than just the natural percentage of days that the stock market went up. But that's okay. Now that we have backtesting, we actually have a lot of confidence in our model and our ability to test it. So the next thing we'll do is add some more predictors to our model and see if that improves our accuracy. All right. So what we're going to do is we're going to create a variety of rolling averages. So if you're just a human analyst trying to predict if a stock will go up tomorrow, some of the numbers you might look at are, is the stock price today higher than it was last week, higher than it was 3 months ago, a year ago, 5 years ago? And you might use all of those inputs to help you determine if the stock will go up or down. And we're going to give the algorithm that information. So what these horizons are horizons on which we want to look at rolling means. So we'll calculate the mean close price in the last 2 days, the last trading week, which is 5 days, the last 3 months or so, which is 60 trading days, the last year, and the last 4 years. And then we'll find the ratio between today's closing price and the closing price in those periods, which will help us know, hey, has the market gone up a ton? Because if so, it may be due for a downturn. Has the market gone down a ton? If so, it may be due for an upswing. So we're just going to give the algorithm some more information to help it make better predictions. And then we're going to create a list called new predictors, which will hold some of the new columns that we're going to create. Okay. So we're going to loop through these horizons, and then we're going to calculate a rolling average against that horizon. And We'll take the mean. And then what we can do is actually create a couple of columns. So one will be called ratio column, and we'll name that column close ratio horizon. So close ratio 2, close ratio 5, etc. And then we'll add it to our S&P 500 dataset, data frame. So all this is going to be is the close price in the S&P 500 divided by our rolling average. So the first time through the loop, this is going to be the ratio between today's close and the average close in the last 2 days. Second time through the loop, it'll be the ratio between today's close, the average close in the last 5 days, and so on. We can also look at a trend, and a trend is just going to be the number of days in the past X days, whatever the horizon is, that the stock price actually went up. And what we can do here is say trend column equals. So what we'll do is we'll use shift again, but we'll shift forward this time. And then what we'll do is we'll find the rolling sum, okay, of the target. So what is this doing? Let's scroll up and find the S&P 500 data frame. So what this is going to do is it is going to, on any given day, it is going to look at the past few days and see the average, the sum of the target. So if we're on January 8th, 1990, it's going to look at the last 4 or 5 days and find the sum of the target. There are only 4 days available. So in reality, we wouldn't be able to compute a rolling sum, but let's assume there's a 5th day here, and it is able to. And it would basically take the sum. So the sum of the number of days that the stock price actually went up. Okay, and then we're going to add these to new predictors. Ratio column, trend column. So let's go ahead and run that. And we should now have some extra columns in our S&P 500 dataset. And you can see there's a lot of NANs. So what's the deal with that? So when pandas cannot find enough days or enough rows prior to the current row to actually compute a rolling average, it'll just return NAN. So this is the close ratio 2, which is based on the rolling average of the 2 days prior to and including the current day. So on January 2nd, 1990, there are no days before this. So it can't actually compute a rolling sum. So it returns a rolling average. So it returns NAN. On January 3rd, 1990, it can, right? It takes the average of this day and the previous day. And same thing with all of these columns. It's a little bit different for trend because you can't include the current day. So here it's looking for 2 previous days. It doesn't include the current day because if it did, you'd be including today's target in that column, which will give you leakage and make your algorithm look amazing, but it's not going to work in the real world. So we're going to get rid of some of these extra columns using drop NA. Extra rows, sorry, with the missing rows. All right, so we now see our data starts in 1993. That's because of these trend 1000 and close ratio 1000 columns. So we needed about 4 years of data to actually compute those. All right, so let's see how these performed. So let's update our model slightly and change some of our parameters. So we'll increase our number of estimators to 200, and we will reduce our min sample split to 50. And we'll keep our random state. So let's go ahead and run that. And then we'll rewrite our predict function slightly. So let me go up and copy and paste this. So here, when you just run .predict, basically the model returns 0 or 1. What we actually want is a little bit more control over how we define what becomes a 1 and what becomes a 0. So we're going to use the predict proba method. And what this will return is actually a probability that the row will be a 0 or a 1. So it'll return the probability that the stock price will go down tomorrow and the probability that the stock price will go up tomorrow. So what we can do is just get the second column of this, which will be the probability that the stock price goes up. And then what we want to do is set our custom threshold. So by default, the threshold is 0.5. So if there's greater than a 50% chance that the price will go up, the model will return that the price will go up. But we're actually going to set that threshold to 60%. So this means that the model has to be more confident that the price will go up in order to actually show that the price will go up. And what this will do is reduce our total number of trading days. So it'll reduce the number of days that it predicts the price will go up, but it will increase the chance that the price will actually go up on those days, which fits really well with what we want, right? We don't want to make a ton of trades. We want to know that when we make a trade, the price will actually go up, but we don't want to trade every single day. That's a way to lose money pretty quickly. And the rest of this function should be the same. So let's run that. And then let's go ahead and run our back test again. And this time we'll pass in our new predictors. You may notice that we're actually getting rid of using the close, open, high, low, and volume columns. And the reason for that is those are just absolute numbers, right? So it isn't super informative to the model. If the price today is $465, it doesn't tell me anything about whether the price will go up or down tomorrow. The ratios are actually the most informative part. What is the price today compared to the price yesterday, compared to the price last week? So that's why we actually took those columns out. All right, so once the backtest is done, what we can do is we can take a look at the value counts again for the predictions. So you'll remember last time there were about 3,000 days where it predicted the price would go down, and about 2,000 days it predicted the price would go up. So that was the value counts from last time. The distribution is very different now. You can see that there's only a few days that we've predicted the price would go up. And that's because we changed this threshold, right? We asked the model to be more confident in its predictions before it actually predicted that the price would go up. And what this means is that we're actually going to be trading, we're going to be buying stock on fewer days. But hopefully, and we're about to find out, hopefully we will be more accurate on those days. So we will check the precision score, and we'll look at our target, and then we'll look at our predictions. So let's run that. And we can see when we buy a stock, so when the model predicts that the price will go up, 57% of the time it will actually go up. So this may not seem great, right? 57% is a failing grade in most places, but it's actually pretty good, especially given that we're just looking at time series data and we're just looking at historical prices of the index. This would actually make you money if you had traded off it from 1993 to the present. Now, would I recommend using this model to go make trades? No. There are things you can add to it to make it more accurate, though, that I'll talk about. But this is actually a pretty good result, given the data that we had to work with. And it's better than our baseline, right? So the stock went up about 53% of the days, but our model is actually, on days it says to buy, the price actually goes up 57% of the time. So the model actually has some predictive value. Okay, so let me summarize and then talk about things you could do to extend this model. So we did a lot, right? We downloaded some stock data for the S&P 500 index. We cleaned and visualized the data. We set up our machine learning target. We trained our initial model. We then evaluated error and created a way to backtest and really accurately measure that error over long periods of time. Then we improved our model with some extra predictor columns. So if you want to continue extending this model, some things I would recommend thinking about. So there are exchanges that are open overnight. So the S&P 500 only trades during US market hours, but there are other indices around the world that open before the US markets open. So it might be worth looking at those prices and seeing if you can actually correlate them, right? If an index on the other side of the world is increasing, does that help predict the S&P 500 better? You can add in news. So that includes articles that are coming out, general macroeconomic conditions like interest rates, inflation, etc. You can also think about adding in some key components of the S&P 500, like key stocks and key sectors. It's possible that, for example, if tech is in a downturn, it's possible that 6 months later the S&P 500 will go down. Maybe it doesn't go down immediately. So that's another thing you can try. You can also try increasing the resolution, right? We're looking at daily data here, but you could try looking at hourly data, minute by minute data, tick data even, if you can get it. Not always the easiest or cheapest to get, but if you can get that data, you can make more accurate predictions. So those are just some ideas on where you can take this. But as I know from personal experience, you can build quite a bit on this model and get pretty far if you want to. All right. So I hope you enjoyed this overview of how to build a machine learning model to predict the S&P 500.